All right, I have started recording the session. So before starting the session, so we are here to discuss the some problems based on the topic that we are going to learn in this course. So this course is entitled "The Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation and its Application in Organic Synthesis." So this is the session which is on the NPTEL or the SOEM platform. So I think it's great initiative because many people they are not belong to IITs, so they can actually learn from the professors which are actually in the IITs. They are teaching in IIT from many years. So this is the course which is generally I mean which is taught in the NPTEL platform by the professor YD Vankar, and he was the professor in IIT Madras for several years, and after retirement, he moved to the IIT Bombay as an emeritus professor. And so this course is deals with the some concepts of the oxidation reduction and carbon-carbon formation, and address some issues of the selectivity, radio selectivity, as well as the chemo and the stereo selectivity. In the stereoselectivity, especially the enantiomeric and diastereomeric, which compound is forming the excess that we'll discuss in this course. And also the problems based on the whichever the reaction that will be discussed in this course. Definitely more focus will be on the solving the problems, and particularly as mentioned by the professor in the itself in the platform. So it is this course is definitely good for the who are preparing for the CSIR, NET and GATE examination. So before starting this all discussion, so I will first introduce myself. I am Vijay Rane. I am a Prime Minister Research Fellow in IIT Delhi, and also I'm a research fellow in the University of Queensland. And this is like a part of our teaching assistantship duty. So, and also I like to teach the students. So this is like also a platform for me to interact with the students and uh, teach the course. So I would like to know if someone tell me actually you are a masters or the PhD students or BSc students. So if anyone, so here there is Ankamwar PR. So sir, can you please introduce yourself, or you can introduce like what you are doing, or are you a master students or PhD student? So
Hi,
hi.
hi, sir. I'm working in the industry, pharma industry, R&D sector.
Oh, all right. Yeah. Anyone who is from the masters?
I'm audible, sir.
Hi.
I'm Jayadurga Reddy, sir. I'm studying Masters of Pondicherry University.
Oh, all right. You are masters from Pondicherry University. All right.
Yes, sir.
Anyone also from I mean doing masters? So Shrikant, and there anyone who is in the first year of the PhD, first or second year? All right. If no one is from the PhD, so also I would like to mention this course is also you can consider as a part of your credit for the PhD. So those who are doing the PhD in the state universities, they can also use the credit of this NPTEL course, and they can show in their uh, evaluation. So I think for PhD they need to complete their 18 credits. So this course will give you 3 or 4 credit. So you can consider that one. All right. So without making delay, so we'll directly start our discussion. So this course is, as I mentioned here. So basically, it deals with we see some oxidation reduction reactions, and also the mechanism of this reaction. So already the professor have completed some of the topics from the week one course, and which mainly deals with the why the organic synthesis is important, and in organic synthesis, why the selectivity, stereoselectivity, as well as the to understand mechanism is important in this case. So here there are two students from PhDs, so Kailash as well as the Shrikant. So welcome you guys, and I hope you will enjoy learning this course. Also in the first week, professor has discussed regarding the sulfur-based oxidation of the alcohols, and particularly focused on the Pomeroy rearrangement as well as the some modifications in the reagents for the Pomeroy rearrangement, and sulfur-based oxidation like Swern oxidation, and also modified Swern oxidation, that kind of reactions that has been discussed. And again, the some organosilane chemistry has been discussed in the fifth lectures of this in the first week. So why selectivity is important? So I would like to highlight. So let's say we have some examples of this one, and we have to selectively, let's say in first case, so I will use the pointer. Let's say here in the first case, we have to oxidize only this bond, not this and this bond. So we have to first understand what is the difference between these three bond, let's say A, B, and C. So here, this A bond, double bond, this double bond is attached to the three different carbon atoms, right? So it is a tertiary double bond. In this case, it is secondary, and in this case, it's a kind of primary double bond. So all these primary, secondary, and tertiary double bond has different selectivity. So if you have to do any reaction on any of this double bond, we can use different reagent, and we can manipulate the or we can selectively oxidize or reduce this double bond. So let's say we have to do the epoxidation, and if we put the metachloro MCPBA per benzoic acid, so MCPBA used for the epoxidation of this double bond, and if we use this MCPBA, so we will get only and we add the MCPBA about one equivalent, so we'll get the epoxidation of this double bond. So why this is? Because this is a tertiary double bond and it is kind of electron rich. So we can selectively do the oxidation. So in this case, epoxidation of this double bond by using this MCPBA. But let's say we don't want to do the epoxidation of this double bond, and we want to selectively do the epoxidation of this primary double bond. Then we have to use the different reagent combination. That all part we are going to discuss in this course. And already professor has discussed some of the example and mentioned this one. So I will not go more detail in that one. Also, let's say take the example of this complicated molecule. The name of this molecule is the Taxol. And you can see there are too many functional group and similar kind of functional group. Let's say here there is alcohol. This is also alcohol functional group, and this is also alcohol functional group. So there are three different OH group. And if you look at each OH group is different. So in this case, what differentiate this OH group? So this OH group is like a secondary OH group. And if you look at addition, there are no any kind of any functional group nearby. But this OH group is the OH which is adjacent to the carbon atom, right? So the reactivity of the OH A and this reactivity of this OH B is definitely a different reactivity. So by using reagent combination, we can distinguish and selectively do reaction or selectively perform the reaction on this kind of complex molecule and this kind of similar functional group, although both are hydroxy group, but this is attached to the carbonyl. So we can selectively oxidize or perform selectively or functionalize this OH. We can convert OH to any OR or OAlkyl or any functional, we can add any side chain to this one selectively. So that's why the selectivity and all this part is important for this course and for our in case of chemist's life, it is important part. And in the first week, I will directly just show the main points and directly go to some problems. I will not solve the problems of the week one because the problems they are the is part of the evaluation criteria for this course. So, but if you have any doubt on the problem, then we can discuss that one. So in the course, in lectures, we have already seen this rearrangement, reactions like Kornbull, the role of DMSO in oxidation reaction. So in the reaction, we learn about the Swern oxidation reaction. So this is also the part of that one. I will just add some slides from the topic from the lectures. Also, this is Moffett and Pitzner. They show the involve of DCC, dichloroperbenzoic acid, in the oxidation, the DMSO based oxidation. Later use of the phosgene, and this is how the Swern oxidation has been evolved. So we'll directly see the mechanism of Swern oxidation, and so you can able to solve the problem based on this Swern oxidation. So what are the reagent used in the Swern oxidation? So anyone?
Auxiliary chloride.
All right, auxiliary chloride. Somehow I'm not able to hear you loudly. All right. So auxiliary chloride is one of the reagents. So the structure of auxiliary chloride is Cl, C double bond O, Cl, right? So auxiliary chloride is one of the reagent. Another reagent is dimethyl sulfoxide, right? DMSO. And these together forms a intermediate in the fashion, like let's say this polarized in this fashion. So S plus and O negative. And this O negative interact with the carbon and release this chloride. So it forms a intermediate like this. Right? And whatever the chloride minus that which get uh, eliminated or get leave from this species auxiliary chloride, so which attacks to this one and which forms intermediate in the fashion of Cl, right? And which has the positive charge. So this is kind of active intermediate, and from this one, so when it attacks to this, it goes to here and later. So it will be CO plus CO2. So it will form, there will be a one of the side product is carbon dioxide, another side product is carbon monoxide, and another one is the chloride minus ion. So these are the three side products which form while the steps. And later, once this active intermediate we got, so when it interact with the, so if we have to do the oxidation of this alcohol, let's say here R2 and the R1. So this alcohol react with this one, the chloride get removed. So it will form CH3S, CH3, later it is alcohol. So, and if there is hydrogen, then this eliminated chloride minus will abstract the proton followed by the double bond formation. So here there was a positive charge, right? So it will form a oxidized product. So this is the general mechanism of this Swarn oxidation. And the similar mechanism is formed in the different modification. So like in case of DCC, it will form the similar manner. This auxiliary chloride, right? So DMSO in the DCC. Uh, so here I have written already. Right. Here there are multiple oxidation reactions are written. So in similar manner, there is polarization in the DMSO, followed by in the Kornbull oxidation. So it interact with the CH2Br, this kind of alkyl bromide or alkyl triplets. So it forms such intermediates, which I have already seen here. So I'll just label this intermediate. So this was the A, let's say. So it forms a intermediate like intermediate B, right? And later, in place of base will abstract the proton. So this was the, let's say, hydrogen. Base abstract this proton, followed by the, in this fashion, it forms the oxidation. So let's say we have the primary alkyl bromide, it will forms the aldehyde. And in case of secondary, it will form the ketones. So DMSO based oxidation like with the any kind of living group. So in this case, so as we seen in this case of the Sorn oxidation, we use the auxiliary chloride, and when you when it react with the DMSO react with the auxiliary chloride, it forms the such intermediate. So this entire group will be a kind of a living group, right? So in this case also, this E stands for, or OE stands for a living group, and when it react with the alcohol, it forms such intermediates followed by the proton abstraction by the base or the any nucleophile from the reaction mixture, uh, which leads to the oxidized product. And there is also a oxidation based on this dimethyl sulfide, and which has this kind of some fancy reagent used. So dimethyl sulfide and these reagents, they react to form such intermediate which have the this chlorine as a living group. So this is how, and if you look at the further steps in this case also, which is similar like Swarn oxidation, or this alcohol react with this group and this chlorine will be will get loose. So all these reaction have the similar kind of mechanism. Only difference is in the living group and the active intermediates. So this is the example that in case of DCC that I have not shown here. But if you look at here closely, so this is the DCC, and dimethyl sulfoxide react with the DCC, form such intermediates, and later it react with the alcohol, uh, and followed by the, here let's say there is hydrogen and any nucleophilic species from the reaction, so which will abstract the proton, and so we'll get the oxidized product. So in all case, the the mechanism is very similar. Only difference is the reagent used. And the drawback of the this kind of reaction, which involve the DCC, is the formation of this dithiourea as a side product. So because of this side product, so people generally don't prefer to use the DCC instead of auxiliary chloride. So in the Sorn oxidation, in many industries, large scale reaction also perform using the Sorn oxidation, but not with using the this kind of reagent. So which involve the DCC because of the side product. Because if you look at the Sorn oxidation, the side products are very crucial to note. So the side products was in this case there is carbon dioxide, carbon monoxide. They all are gases. So if you just bubble the reaction or the whatever the reactor with the inert gas, let's say argon or nitrogen. So these all CO2 and carbon monoxide get released, get separated from the our reaction vessel, and we get the product. But in case of when you use the DCC at that time, this this was the dithiourea. Sorry, this as the intermediate. This intermediate is sorry. This side product was the crucial, and removal of this one was the difficult. That's why people don't use the DCC. Use the alkyl chloride. So those who are preparing for NetGate, this is very common question. So side product of the Sorn oxidation are generally, I mean, if you look at the previous papers, then you make see there was a significant questions based on the side products. All right, so we already seen these oxidations, sulfur DMSO based oxidations, and I already seen every reactions has the same reaction mechanism. So in this case, there is DCC. We already seen the structure of the DCC here. So this kind of pyridyl sulfonate, alkyl chloride, uh, acetic anhydride, or tryptilic anhydride. This kind of also living group or the reagent used for the this kind of DMSO based oxidation, and which will be act as a living group in this one, in this case. And another Cumberland type of oxidation, which doesn't involve any kind of such a living group, but the starting material itself should have the such living group. Like in this case, there is bromide. So in this case, if you look at the example, so dimethyl sulfoxide forms such kind of polarized species, which react directly with the uh, starting material and removes the bromide. So in this case, there will be any kind of bromide, and which forms such intermediates. Later, this Br minus just abstract the proton here, or Br minus or a base present in the reaction which abstract the proton, and we get the oxidized product. And here, this is dimethyl sulfide will get as a side product. So this already seen the mechanism of the Sorn oxidation. So I don't think we need to go in more detail in that one. So these are the some important uh, some examples based on the DMSO based oxidation. So we'll move toward the Pomeroy rearrangement. So we'll first see the mechanism of the Pomeroy rearrangement, and then we'll see other problem based on this rearrangement. So if you look at the uh, Pomeroy rearrangement, so this kind of starting material in presence of acid or base and co-catalyst forms such intermediates which involve this active intermediate, and when the nucleophile interact with this this kind of intermediate. So we get the RSH as one of the product and oxidize nucleophile. In this case, there will be alcohols. So when we have the alcohols, let's say secondary alcohol R1, R2, sorry, R3, R2, and the alcohol. This alcohol again, as like we've seen already, uh, interact with such intermediates and forms a keto, and we get uh, this RSH as a side product, and this is the mechanism. So here, in this case, I will directly, I will show the mechanism. We'll discuss the mechanism here. So let's say we have the intermediate, sorry, the starting material, which has the sulfoxide, which has the alpha CH2 here, and which react with the uh, acetic anhydride, right? Better I will take it on the new slide. So we have a sulfoxide, which has the, so there, the requirement is here. Here it says should be a hydrogen, right? So R2 that we already, Professor has already discussed in the lectures, and we have the acetic anhydride. So, so in this case, so let's say there will be a partial charge separation in this starting material, which forms intermediate like this, and this negatively charged species is then react with this, followed by the elimination of the acetyl anion, right? So CH3 double bond O minus, this get eliminated, and and these both two species form a product in this manner, right? And later, sorry, I just missed the oxygen right from here, right here, and there is the sulfur positive. So, and so next step will be the formation of the abstraction of proton. So here there was a CH2. So the condition for this reaction is there should be a alpha CH2, right? So if you look at the questions from the week one, so there are some questions that you can easily solve by from this mechanism. So here hydrogen should be merged, right? In this case of uh, rearrangement reaction. So in this one, the acetyl that was removed initially, I will just write the short form of this OAC minus. So it abstract the proton, followed by the, it forms a carbon intermediate. So here, so we get here in this case R1. So it will forms a, intermediate in this fashion, and because this negative charge goes here, right? So that positive charge on sulfur will, I'll just write, it abstracts the proton, it forms a negative charge, although it will make confusion. So this just goes in this one. So positive charge on the sulfur get vanished. So we found it forms a double bond. And once it forms the double bond, this will get eliminated, right? So it will form two intermediates. I will just write directly here. So it will have the positive charge and another intermediate. R2, right? So, so what happened in this one? So these are the resonance structure. So let's say this moves bond here. So the positive charge get vanished, but the positive charge will comes on the carbon. And when it react with the nucleophile, so let's take the example of the, again, the alcohol, which has the two R groups. So when it react with the alcohol, so let's say this intermediate react with the alcohol, and as like the previously that we have seen, uh, it forms the keto as well as the RSH as a side product. And here nucleophile in this case is equal to a alcohol. So this is the some complicated mechanism of this pulmonary rearrangement. But main thing is essential in this pulmonary rearrangement is the if you look at the closely the structure, this sulfoxide, the hydrogen presence of this hydrogen is essential. So there are some questions based on this one. So I will just show the questions from the week one assignment, and that you can easily solve based on this one. So I will just show directly the question. Where are right? All right. Uh, in this one, so the compound that permit Zorn oxidation of alcohol. Not this one. I think that you can easily solve. Don't consider these answers. They are like I just deselected all this one. So make sure you not take the answer from this one because they are all are wrong. All right. So there was some questions. Let's say here the compound that permits Zorn oxidation of alcohol. You can easily click this one, right? This is the wrong answer that I have selected. So you make sure you don't not select the answers from this one. Right? Because you have already seen the mechanism of the Zorn oxidation, so you can easily. And here also it will be a multiple. It can be multiple answer. So make sure whichever the possible options that you can select. Let's say in this case, I will tell you directly. So you can select these all three. So and this will not show the Zorn oxidation. So in this way, you can select the uh, answers in this one. Again, there was question from based on the pulmonary rearrangement, right? This is the question. So the following molecule which cannot undergo pulmonary rearrangement is. So in this case, which molecule doesn't have the alpha hydrogens? So in this case, I will just. So can you able to see my screen? Right. In this case, you can see here, this molecule have the alpha hydrogen. This molecule also have the alpha hydrogen, and this molecule doesn't have the alpha hydrogen. This also doesn't have any alpha hydrogen. So among these, which molecules cannot undergo pulmonary rearrangement? Cannot. So the compound which doesn't have the alpha hydrogen is definitely not able to go the pulmonary rearrangement. So these two will be the answers for this one, right? So in this way you can solve the problem. Also, we have discussed the mechanism of the Sorn oxidation, right? So you will able to solve the first question also. Again, there will be a question on the uh, Kornbull oxidation, right? So Kornbull oxidation involves. So we have already seen in the slides. So this is the slide that we have already seen. So Kornbull oxidation involves. You can see here. So what it involves. So hope you will get the answer from this one. So you can easily select the answer for. If you look at the options, they have given an SN2 reaction of DMSO and substrate having leaving group. Second option is reaction of methyl sulfide with the N chlorosuccinamide. This is definitely a wrong option. Then again, there is option of SN1 reaction of DMSO with tertiary alcohol. And fourth option is the reaction of dimethyl sulfide with the epoxide. So you can select the option from this one. So if I will be in your place, I will select this option, right? So reaction of DMSO with the substrate having leaving group. So you can see here from the slide. So the reaction of DMSO, right, with the substrate which has the leaving group. In this case, bromine, in this case, triplet, or any kind of such leaving group. Let's say halides, triplets, tosylates, this kind of leaving group. So Kornbull oxidation will be possible in that kind of substrate. Another question is incorrect statement with the with regard to don't consider these options are correct. So incorrect statements with regard to the Moffat Pfizer oxidation, right? So if you look at this Moffat Pfizer oxidation, so that already right here. So you can see Moffat Pfizer oxidation which used in all the use of DCC along with the DMSO. So you can select the correct option based on this one. So whichever you feel correct in this one, you can select that option. The next question is major product formed in the following reaction. So hope you will solve entire question and then you will select the options from this one, right? So I don't think there will be any difficulty in solving this question. So this is the example of the Sorn oxidation reaction, right? Another is permeable rearrangement that also we have discussed already. Next question is based on the same permeable rearrangement. And this is based on the EMCPBA oxidation. So this question also you can able to solve, I think. And last question is, I think this question we should solve because this is not already taught in the lecture 1 videos. So we'll discuss this question and we'll leave other question up to you. So you should able to solve other questions. I'll just all right. So we have the 8th question. Uh, I think we have not seen this in the week 1 videos, right? So here they have given a chair form of this one, and the question given is like in the following reaction. In the following reaction, although the starting ketone is racemic, it has log conformation with third butyl group in equatorial position. So let's say starting material is racemic, And the nucleophilic addition of this methyl magnesium bromide is highly stereoselective, leading to the formation of A as a major product and B as a minor product. So in this case, A as a major product, right? And B as a minor product. Then correct statements about the products are. The correct statement about the products are. So in this case, so don't consider this answer will be correct. So these are the four statements A, B, C, and D. So the which statements about this one is the correct. So in this was in this reaction, as we see, methyl magnesium bromide is like Grignard reagent, right? So it will add selectively as mentioned in this one, highly stereoselective. So if you look at the structure, so this keto will be the methyl magnesium bromide will attack from the here there will be hydrogen, right? So methyl magnesium bromide attack, let's say from the downside, then it form the product A as a major product, and if you attack from the upside, then the product B will form as a major product B, right? And also in the question it is mentioned the A as a major product. So A will be a major and B is the minor. Then correct statement. So first one is statement given. A and B both are optically pure. So if you look at the statement here, already in the statement is mentioned the starting ketone is racemic. So there will be two possibilities. So this terbutyl will be in this hexane, right? This is the if you look at the structure. So in one case, this TBU will be downside. In another case, so this TBU will be from downside. If you look at in the two-dimensional side, and if it is racemic means these both are present in the equal amount. Then A and B both are optically pure. So obviously this option should be neglected because if you are using the racemic one, then there is no chance to get the optically pure compound. The second one is mentioned A is optically pure, B is not. So in this one mentioned the major product form and which formed by the attack from the downside will be a major product. But if you look at the structure in this one, so already it is mentioned this is A if we are using a racemic mixture. So definitely both will the product will form will also be the racemic because this is 50%. But the another possibility is this will also be 50%, right? And the reaction by the downside attack, like let's say in this case, attack from the backside and attack from the front side, these both will form a same product. And another one, the in this case, attack from the front side and attack from here from the back side will form the another product. Let's say this will be let's say X and this will be Y. I'm not sure which will form A or B by the upside attack or backside attack. But if you have the racemic starting material, and then we are doing the reaction which form the two product, so the both will form a racemic mixture. So in this case, most probable answer will be a racemic. So does anyone have any uh, clue here which will form a major product or which statement is correct in this all four? So if you have answer, you can. It is like this session is about this session. But if you look in this case, in this one, if you go in the more detail of this addition of this Grignard reagent on the starting material which has the third butyl group, so there are definitely too many possibilities are open possibilities because uh, the starting although starting is racemic, but the form products will be only there will be only two products will gonna form. and it might be both will be optically pure. So we can't say. So we have to go more detail in the mechanism, and I think that will be discussed in the next video by professor. So as of now, uh, among these four options, so we can't neglect any one of this one, but we can neglect only these two, the option B and C. So option D, sorry, A and D will be the most probable option among these two. There will be 50-50 chances. So if anyone have any answers, you can tell us right now. So we'll also I will also interested to know how you are approaching this question. So anyone have any answers for this one? Alright, if you don't have any option as of now, I think you should select any one of this one, A and D, or it's up to you. This question counts in the marking, so I don't think it's good idea to tell the exact answer for this one to you. But I think you should try this one. We'll see the more problems from the week 0, which is not involved for the evaluation. So there are some questions that we can easily solve, and they are not already the deadline for solving this question already gone. So we can solve these questions. So there is one question based on the alpha beta unsaturated ketones. So in this one, alpha beta unsaturated ketone, right? So let's say there is any kind of functional group reagents combination that used to carry out epoxidation of alpha beta unsaturated ketone. So in this case, I think answers are already there, right? Alright, if answers are not given, then I will tell you some answers. Otherwise, you can follow the answer there. So in this case, the answer will be alpha beta unsaturated ketone. And if you have to do the uh, if you want to carry out the epoxidation of alpha beta unsaturated ketone, epoxidation means the formation of this uh, right. So R, let's say here H, and we have to perform the epoxidation of this double bond. So the proper the reagent combination here in this case will be hydrogen peroxide and sodium hydroxide will be the correct option in this case. Because if you use the metachloroperbenzoic acid, it will form the have you heard about the rearrangement reaction with the metachloroperbenzoic acid? Rearrangement of the ketones with the MCVPA. So there is high chances of formation of that rearrangement. Another question is the on the major product forming the following reaction. So if you look at this reagent, this is the reagent of Birch reduction reaction, right? And so here they have given the acid. Acid is like electron withdrawing group. So you can easily able to get the answer from this one. So let's say we have the normal benzene ring which has the electron withdrawing group. Let's consider it as a carbonyl carbon as a sorry carbonic acid as a electron withdrawing group, right? Because it withdraws the electron. So it will be a electron withdrawing group, and if you perform the Birch reduction reaction of the electron withdrawing group, which product will be formed as a major product in this case? So I will directly show the mechanism here. So if you have the electron donating group and electron withdrawing group, the mechanism will be different in both the case. And mechanism is different because uh, the stability of intermediates. So let's say we have the R, in this case, electron withdrawing group, and when it forms the electron, when it takes the electron. So if you look at the Birch reduction reaction, this metal will be the lithium, with the triethylamine, it forms the lithium cation, right? Lithium cation plus electron, and these electrons will be solvated electrons. That is the electrons and solvated with the ammonia, right? We use this reaction at minus 78 degrees Celsius because to stabilize this electron, right? So this electron, when we it get into the aromatic ring, so this will be the first this electron attack on the, let's say, para position, and it will be because of the rearrangement, it will forms a radical at the center and anion at the center para to the electron withdrawing group. And again, the it when it react with the this intermediate react with the alcohol, because we add the alcohols in the Birch reduction reaction, right? You can look at the reaction condition also here. So in this case, they have added ethanol, right? And to quench the reaction, they added later the water. They initially the water is not present, only the lithium plus ammonia in the THF, and after 15 minutes they add the if you perform reaction after 15 minutes we add the ethanol. Then the further reaction occurs. So the first step is the formation of electron, the and stabilization by using the triethylamine. So this will be the first steps get formed, and when you add the and once it form, it directly this electron free electron directly attack to the aromatic ring. It form the two type of intermediate. So in this case, another case, there will be a when there will be electron releasing group or electron donating group. In that case, it forms the negative charge to the ortho position and radical to the meta position, followed by uh, the reaction of this intermediate with the alcohols in both the cases. So it forms the radical which is stabilized by the. So in this case, when there will be an electron withdrawing group, the radical will be stabilized uh, in the ipso position, and then there is the electron donating group. Radical is stable at the meta position. That's why we get the two different product in this manner. So when there is electron withdrawing group, you can simply those who are preparing for NET and GATE examination, when there is electron withdrawing group, it forms a product like this, and when there is a electron donating group, it will form product in this manner. So these are the product when there is electron withdrawing group. So electron withdrawing group is like any acid. So let's say this is the acid or aldehyde, or let's say there is a kind of keto, this kind of, or cyano or nitro, this kind of any group, which will form the product in this fashion, which has the double bond in this manner with respect to the electron withdrawing group. And when there is electron donating group, the product will be in this manner. So you can able to select the correct answer from this one. So here in this case, electron withdrawing group, right? So this will form the option number 4 as a product. There is another question which involves the question states we have the optical active molecule A is hydrogenated in presence of palladium on carbon. So if you look at the reaction of the palladium on carbon, so the steps involved. So let's say we have the double bond. When the palladium on carbon, the and we add the hydrogen as a when it react with the hydrogen, it will forms the absorb traces, right? So hydrogen will be absorbed on the palladium catalyst, and later when it goes in contact with the olefin, so it will forms a intermediate in this manner. So it will be on same side. So both hydrogens will be on the same side of this olefin, and we get the hydrogenated species. So both the hydrogen will have the same stereochemistry in this case. So if you look at this question, this starting material and this starting, and we perform the reduction H2PDC reduction. So someone given the answer, it should be option number 3 in last question. Last question, which question? The question, can you, the question number 3? Oh, sorry. Right. Sorry, by mistake, I have just selected this one. The option number 3, right? So because we have already seen, right, electron withdrawing group, so the option number 3 will be the question. I will just consider this like vertically. Correct. So the option number 3 is the correct option in the case of Birch reduction. The question. Okay, let's move to our this question. The fourth question. In this question, we are performing the H2PDC reduction, right? And as we've seen in the mechanism, the addition of this hydrogen will occur on the same side. So in this case also, let's if you perform the addition of this one, so here there will be a double bond, and we are performing reduction. So if you look at this one, so in this case, what we can see, this hydrogen and this hydrogen, one hydrogen is equatorial, it's both the equatorial, but one is directing upward and one directing downward. So this will not the correct option answer. In this case, one hydrogen is axial, one is equatorial, and both directing upward. So this will be looks a correct option. We can see remaining two options. In this one, if you look at the geometry of this one directing downward and one directing upward, that is both are equatorial, but they are anti to each other, right? So this is obviously the wrong option. And in this one, as we see here, there will be a one is directing upward, another also directly upward, but they are seen to or on the same side to the this carbon group. But if you look at the addition, this entire subset that have to come in close contact with the starting, right? This entire intermediate. So entire this part have to come close to the starting. And if there is this CHO, that is a group which is at axial position or 1,3 position in the chair form. If you look at here, this is 1,3 position, right? With respect to this hydrogen. So there will be a lot of steric crowding. So that's why this option will be not right. And in this case, the option A is the correct option in this case. Because if you look at this CHO, it is axial to each other, axial. And this addition of this hydrogen also axial as well as directing upward. And this hydrogen, both hydrogens are on also on the same side. But if you look at this entire bulky, the palladium substrate with the hydrogen, they are when they come in close contact with this one, so there will be a lot of steric repulsion between this one. So that's why this option is not the correct option. So the option number B is correct option in this case. So this was the some question from the week 0, that just for the get the favor of the how the assignment and all works. So this was the some question the professor had put in their week 0. So another next question is like based on the this is the one of the rearrangement reaction you probably know better than me because you are updated. So here you can see this is the acid reaction of acid with the diazomethane, right? So this is the diazomethane. If you just Google it, the reaction of acid with the diazomethane, you will get one of the rearrangement reaction, name of the one of the rearrangement reaction. And so what forms in this rearrangement reaction? If you go to the mechanism of this one, so this diazomethane, so if you just split the structure, this is the nitrogen and there will be a double bond and nitrogen. So this will be a positively charged nitrogen, right? And this will be a negatively charged. So am I audible? I just lost my connection probably. Right. So this is the structure of the diazomethane. And in this case, so this diazomethane and acid, they forms, if you look at the mechanism, I will just bring the mechanism of this. I will just, for a moment, pause. All right. So here is the exact mechanism for this one. So what happens? These acids, this CH3 abstract the proton and it forms the O negative, right? So there will be a pH CH2 double bond O negative, and the another intermediate forms from this diazomethane. After abstracting the proton, it will be CH3 N double bond, sorry, N triple bond N, and here there will be a positive charge. And after this one, what happens? The negatively charged, this will attack here, and this is as a leaving group, right? Because nitrogen already have positive charge, so definitely this will be a good leaving group. When this O negative attack on the carbon, it will form a PHCH2 double bond O CH3, the ester as a product. So this is the rearrangement reaction. And if anyone know the what is the name of this rearrangement reaction, so the product form in this case will be a ester. So this CH2, this PHCH2 C double bond OMe, this will be a product form in this reaction. So anyone know what is the name of this reaction?
Aryan ester.
Sorry, can you repeat?
Aryan ester formation. Aryan
Right.
ester.
So this is the name of the reaction. And another question is based on the stereochemistry. So these are not correct answer that I have selected. So another question based on the stereochemistry. So the absolute configuration of these asymmetric centers. So anyone, you can easily solve this one, I think. If you look at the center A, so which has, I will just select Br, C double bond O, H, H, and the another group which has the CHOH, CH2OH. And if you give the numbering to this one, so the Br will be the first priority, this COH will have second, and this will have the third priority. So it will be a clockwise, right? But the hydrogen, the fourth priority group is on the horizontal. So clockwise R changes to S, right? Because the fourth priority group is on horizontal position. So the A has the absolute configuration S. The another one is the B center. B center have the hydrogen here, the OH here, followed by the CH2OH, and there will be C, H, Br, and COOH. So the first priority will goes to the hydroxy. Second priority will goes to the group which has the carbon and the bromine. Third will have this one, and the fourth. So if you look at this one, 1, 2, and 3, that is S anticlockwise, which changes to R. So the correct option will be here SR. So you can select any one of this one. So right. So the SR will be, this will be the correct option in this case. So this all part, no need to worry as of now. We are going to see in the later part of this course. So all right, anyone have any doubt in this case? Hope you will able to solve all the problems based in the week 0 as well as the week 1 of this course. There are some more problem. If you look at the first question from the week 0, and I will just directly take it into the, although this we have not already discussed in the week 1, but there are some problems given in the week 0. They are from the later part of this course. So this course is mentioned per acids such as parasitic acid or metachloroperbenzoic acid. Let's take the example of MCBA. Readily epoxidize the isolated olefin from cyclohexene. Let's say there is cyclohexene, but they do not epoxidize an alpha beta unsaturated ketone. Let's say we have the alpha beta unsaturated ketone. No need to consider the cyclohexane in this case. If it is any simple alpha beta unsaturated, that also okay. All right. So if you have such alpha beta unsaturated ketone or any R here, why? This is because the MCBA why easily epoxidize this one, but not this one. So the main reason for this one is the if you look at the mechanism, what happens in the MCBA. So if you look at the structure of this metachloroperbenzoic acid, I will directly put from the Google. Right. So this is the structure, and from the structure, if you look at the attachment of this oxygen, which attached to the hydroxide as well as the carbonyl group, both are electron withdrawing group, and how the reaction works for this one. So this O will comes in the contact with the, let's say this is AR that I am writing. This comes into contact with the double bond, and so when it comes in the contact with the double bond, the electrons, the let's say positive both electrons from the double bond are get involved in the formation of the bond between this and this. So we get the product which has the these bonds. So the oxygen is not utilizing the electrons because it is attached to the, not readily utilize its electron because it attached to the both electron withdrawing groups. That's why when there is electron rich olefin present, at that time the epoxidation happens easily. So in this case, the answer, the question itself mentioned the metachloroperbenzoic acid readily epoxidize the isolated olefins, that is isolated double bond, but not the alpha beta unsaturated. And if you look at the alpha beta unsaturated olefin, this is electron deficient because it is attached to the electron withdrawing group. So it is electron deficient. That's why it is not react with this, but it readily react with the isolated olefin. So the correct option from this one also you can easily select. So an isolated olefin is electron rich and per acids is electron deficient. This is the correct option. The second option is the per acid is electron rich and thus react with the isolated olefin. Wrong. Alpha beta unsaturated ketones is electron rich. This is obviously wrong. Electron rich, not electron rich. It is electron deficient. The per acids is electron rich. This is also wrong. And alpha beta unsaturated ketone electron deficient. per acids are electron rich and alpha beta unsaturated are electron deficient. These all statements are wrong. The option one is the correct option in this one. So in this way, you can able to solve all the questions. All right. Hope you have enjoyed the session. So this was my first session from this course. So probably ignore this handwriting as of now. Hopefully next I will get habituate this with this kind of writing. Anyway, so hope you guys don't have any doubt regarding the assignment questions, right? So should we stop here? All right. We'll stop here for now. And thank you so much for joining.